Piping vibration mainline corrective actions, effective strategies to address primary system issues. This topic refers to guidelines for the avoidance of vibration-induced fatigue failure in process pipework by Energy Institute. Purpose and approach of mainline corrective actions. Mainline corrective actions are essential strategies implemented to mitigate vibration, pulsation, and dynamic stress in piping systems. These actions are categorized into two primary groups, those targeting the excitation mechanism and those addressing the response mechanism. The excitation mechanism refers to the source of energy causing vibrations, such as turbulence, pulsation, or mechanical forces. By reducing or eliminating this energy, the system becomes inherently more stable. Conversely, response mechanism actions focus on altering the structural characteristics of the pipework to withstand or dampen the induced vibrations. This can involve changes in stiffness, mass, or damping properties. The preference is always to address the excitation source first, as this prevents energy from entering the system. However, when this is not feasible, response-based solutions are applied to manage vibration levels effectively. Detailed predictive techniques, such as those outlined in Technical Module 09, and specialist measurement methods from Technical Module 08, are often required to validate the effectiveness of corrective actions before implementation. These analyses ensure that modifications do not inadvertently introduce new resonance issues or compromise system integrity. In complex systems, multiple excitation mechanisms may coexist, necessitating comprehensive solutions that address all contributing factors. Ultimately, the goal of these corrective actions is to enhance reliability, reduce maintenance costs, and prevent catastrophic failures caused by fatigue or excessive vibration. General pipework corrective actions, support adjustments and contact prevention. General corrective actions for pipework focus on improving structural support and preventing harmful contact. Tightening clearances on existing supports is a common method to increase pipe stiffness and raise its natural frequency, thereby reducing vibration levels. This approach works because energy levels typically decrease as frequency increases, making the system less susceptible to resonance. However, thermal expansion must be considered to avoid overstressing the pipe during temperature changes. Another critical measure is avoiding metal-to-metal contact between moving pipe sections and structural elements, which can lead to fretting damage. If contact is unavoidable, inserting wear-resistant or compliant materials between surfaces can mitigate wear. Alternatively, redesigning supports to eliminate contact points is recommended. These actions not only reduce vibration but also extend the lifespan of the pipework by preventing localized damage. Care must be taken when altering support stiffness, as changes can inadvertently align structural natural frequencies with excitation frequencies, creating resonance conditions. Therefore, any modification should be preceded by a thorough analysis of the system's dynamic behavior. Flow-induced turbulence, excitation control, response modifications. Flow-induced turbulence is a major source of excitation energy in piping systems. Reducing fluid velocity is one of the simplest and most effective solutions, achievable by increasing pipe diameter, adding parallel lines, or adjusting operating conditions. Lower velocities reduce turbulence intensity, thereby minimizing vibration. Flow smoothing techniques, such as using swept tees instead of 90° tees, minimizing bends, and incorporating long radius bends, further reduce turbulence. Flow straighteners can also be installed to stabilize fluid movement. Valve selection plays a critical role. High recovery valves with streamlined internal contours dissipate less energy, reducing downstream turbulence. Examples include rotary control valves like eccentric plug, butterfly, and ball valves. Additionally, changing valve trim can help control kinetic energy at the trim exit, ensuring it remains within safe limits for continuous or multiphase flows. These measures collectively aim to reduce excitation energy at its source, preventing excessive vibration and prolonging system life. Let's see this diagram on the left. This diagram shows how turbulent kinetic energy is distributed across different frequencies, illustrating that most of the energy in a turbulent flow is concentrated at very low frequencies. As we move to the right along the frequency axis, the energy drops rapidly, starting from very high values near 10,000 and decaying in a steep downward trend. The oscillations we see in the mid-frequency range represent the presence of coherent eddies and fluctuating flow structures, but overall, the curve continues to taper off smoothly. By the time we reach higher frequencies above 50 Hz, the energy becomes minimal, showing that small-scale turbulence contributes far less to the total energy. In summary, this figure highlights how large, slow-moving turbulent structures dominate the energy spectrum, while higher frequency motions carry progressively less energy. When excitation cannot be sufficiently reduced, response-based solutions are applied. Increasing support stiffness raises the pipe's natural frequency, reducing its susceptibility to turbulence-induced vibration. However, thermal growth constraints may limit additional supports. In such cases, viscous dampers provide effective damping across a range of frequencies while allowing thermal movement. Unlike conventional snubbers, these dampers are designed for dynamic vibration control and require specialist advice for proper installation. Shock arresters can also be used to resist sudden movements caused by forced vibration, though they require regular maintenance to ensure functionality. Composite pipe wraps offer increased stiffness and damping but should be used cautiously due to limited knowledge of their long-term fatigue resistance. Increasing pipe wall thickness is another option, as it enhances structural inertance and reduces dynamic stress levels. These measures collectively strengthen the pipework's ability to withstand excitation forces, ensuring operational stability. Let's see this diagram. This diagram compares the vibration response of the pipework before and after a viscous damper was installed, showing a dramatic reduction in velocity across the dominant frequencies. The blue curve represents the system without a damper, where we see a strong resonance peak near 2 Hz reaching over 20 mm per second RMS, indicating significant vibration. After the damper is installed, shown by the red dashed line, the peak at this frequency is substantially suppressed to below 5 mm per second, and similar reductions occur at the smaller peaks around 4 to 6 Hz. Across the entire frequency range up to 15 Hz, the damper effectively lowers the vibration amplitude, demonstrating how the added damping dissipates energy and stabilizes the pipework response. Overall, this figure clearly illustrates the damper's role in mitigating resonance and improving system reliability. Managing mechanical excitation, response tuning techniques. Mechanical excitation often arises from rotating machinery or connected equipment. One effective corrective action is changing the operating speed of machinery to avoid resonance with pipework natural frequencies. This adjustment must be carefully analyzed to prevent introducing new resonance conditions. Isolation mounts are another solution, decoupling vibration sources from the rest of the system. These mounts are most effective when installed during the design stage and require a stiff foundation to function properly. Bellows can also be used to break vibration transmission paths, though they introduce additional considerations such as pressure drops and potential turbulence. Each of these measures aims to reduce the transmission of mechanical energy into the piping system, thereby minimizing vibration and associated fatigue risks. Let's see this diagram. This diagram illustrates how a pipe's fundamental natural frequency changes with both its span length and outside diameter. As shown by the shaded bands, longer spans tend to lower the natural frequency, while increasing the pipe's outside diameter raises its stiffness and therefore increases the natural frequency. For example, pipes with long spans in the upper shaded region fall near 1 Hz, indicating they are more flexible and susceptible to low-frequency excitation. As we move downward through the bands, from roughly 4 Hz to 7 Hz and finally into the 14 to 16 Hz range, we see that shorter spans and larger diameters produce progressively stiffer pipe systems with higher natural frequencies. Overall, this figure helps demonstrate the structural relationship between geometry and dynamic behavior, allowing us to understand how design choices influence a pipe's vibration characteristics. Response tuning involves altering pipework characteristics to shift natural frequencies away from excitation sources. This can be achieved by adding stiffness or mass to the pipe, depending on whether the goal is to raise or lower the natural frequency. For example, clamps or additional supports increase stiffness, while added mass lowers frequency. Modifying span length or pipe diameter also influences natural frequencies significantly. These changes must be carefully planned to avoid coinciding with harmonic excitation frequencies, which could create new resonance issues. In systems with variable excitation frequencies, caution is essential, as operational changes may reintroduce resonance. Proper analysis and monitoring are critical to ensure long-term effectiveness of these modifications. Pulsation and acoustic issues, reciprocating equipment pulsation, high-frequency acoustic excitation. Reciprocating pumps and compressors generate pulsations that can excite acoustic resonances in piping systems. To mitigate this, operating speeds should avoid coincidence with acoustic natural frequencies, typically by maintaining a plus or minus 20% separation. Adjusting line length can also shift acoustic modes, reducing resonance risk. Pulsation bottles and nitrogen precharged dampers are commonly used to attenuate pressure fluctuations, though their effectiveness depends on proper design and maintenance. Orifice plates and acoustic absorbers, such as tuned side branches, provide additional damping for specific frequencies. These measures aim to control pulsation energy and prevent excessive vibration in connected pipework. Let's see this diagram. This diagram shows the significant reduction in dynamic pressure achieved by installing a pulsation bottle on the system. The red bars represent the acoustic pressure levels before the modification, where both the C3S85 discharge and the recycle line exhibited high pulsation, with the discharge point reaching close to 120 bar RMS. After the pulsation bottle was installed, shown by the green bars, the dynamic pressure dropped dramatically to only a small fraction of the original values, down to below 10 bar RMS at the discharge and similarly low levels on the recycle line. This large reduction clearly demonstrates how the pulsation bottle effectively attenuates pressure fluctuations, resulting in a much more stable and controlled operating condition. High-frequency acoustic excitation poses a significant fatigue risk, particularly at circumferential discontinuities. Reducing mass flow rate or outlet Mach number can lower acoustic energy at its source. Using low-noise valve trims, such as multi-stage pressure drop designs, further mitigates noise generation. Increasing downstream pipe length provides natural attenuation, reducing energy levels before reaching sensitive locations. Structural modifications, including increasing wall thickness, removing discontinuities, and adding stiffening rings, enhance resistance to high-frequency stresses. These actions collectively reduce the likelihood of acoustic fatigue failures and improve system durability. Surge control, cavitation and flashing mitigation. Surge events occur during rapid valve operations or pump startup/shutdown, causing sudden changes in fluid momentum. Corrective actions include slowing valve closure times, using soft start pumps, and installing surge relief devices such as fast-acting valves or bursting discs. Surge tanks can also be employed to absorb pressure waves and reduce transient forces. Minimizing bends and using long-radius elbows further decreases energy transmission to the pipework. Viscous dampers provide additional protection against broadband forced vibrations associated with surge events. Cavitation and flashing occur when local pressure drops below the fluid's vapor pressure, leading to vapor bubble formation and collapse. These phenomena can cause severe vibration and pitting damage. Corrective actions include reducing flow rate or fluid temperature, selecting valve types that minimize cavitation risk, and using anti-cavitation trims or multi-stage pressure drop designs. Staging pressure drops across multiple valves or orifice plates further reduces cavitation potential. Flow smoothing techniques, such as using swept tees and long-radius bends, also help maintain stable pressure profiles. Supporting downstream pipework can limit vibration effects, though eliminating cavitation at its source remains the priority.